So from the beginning of this session, we heard how IGN work. We have heard how many IGN we have. And I'm going to show you how IGN looks like over a broadband point of view. In particular, I'm going to show you a few results from a paper we have in preparation on the ultraviolet quasi-composite from WFC3. But before doing that, I'm going to show you the broadband quasi-spectral energy distribution of a type 1 and an obscure IGN. This is an exquisite type 1 with exquisite data from Cosmos. And as you can see, there are basically two gaps, one in the far infrared and the other one in the optical UV. But the one in the far infrared, or millimeter wavelength, will refill my Hall mass. So actually, I really don't care much about this gap as long as you get your proposal accepted. However, at this wavelength, you have absorption by neutral hydrogen along your line of sight, which makes detection really challenging. And I'm going to guide you on a journey on this broadband quasi-spectral energy distribution as my introduction, and I'm going to focus on the optical UV part. So let's start from the X-ray. So we are very close to the black hole. This is what is called the X-ray mysterious corona, which is a plasma of relativistic electrons that Compton scatters photons coming from the disk. Moving outwards, we have emission from the what is so-called big blue bump. And if you have clouds, we are in the inside part of the broadband region. You have also, on top of the continuum, high ionization broad emission lines, such as carbon-4, helium-2, oxygen-6. We are on the order of 1,000 Schwarzschild radius. Of course, less than 1 parsec. We are still less than 1 parsec. Moving outwards, you have low ionization broad emission lines, such as magnesium-2, Balmer lines. And we are of the order 10 to the 5 Schwarzschild radius. All of this emission gives you the big blue bump. But now you are reaching this point. Do you have time? But now we are reaching this point, the 1 micron deep, which tells you what is the sublimation radius of the dust, which is around 2000 Kelvin, 1600 Kelvin for silicates and graphite. So, moving outwards, you have more clouds. Now we have dust. And the optical UV emission that is coming from the accretion disk is reprocessed by the dust in the mid-infrared and near-infrared wavelength. Up to, and the scales that I are here are around, few tens of parsecs. Now we have far infrared continuum, as you can see here from the Herschel data. This is emission from molecular dust at temperature of about 20 Kelvin, CO lines, H2 regions, star-forming regions. This is what we actually think. And this is the transition region between the IGN and the galaxy. We really don't know what is the fraction of IGN and this wavelength. And finally, the bulge. So, and of course, the bicon extended narrow emission line regions. The galaxy, the whole stellar population peaks around 1 micron. This is degenerate with, well, for high luminous IGN, this is not a problem. For low luminous IGN, this might be a problem, but this is extremely bright. And if you move outwards, then there is the galaxy, up to 10 kiloparsec. So this is what an IGN and the emission of the IGN. So the emission of the IGN is actually telling you something more about the physics. So let's go back to this. And I told you that I'm going to focus on this small part, which actually provides you more than 70% of the emission. However, this emission has to be corrected for absorption of hydrogen along your line of sight, and I told you that this is challenging. Why this is important, we have heard already about the classical Sultan argument. So the luminosity of a QSO is tracing the accretion onto the supermassive black hole, and the buildup of supermassive black hole is a fundamental ingredient in all galaxy black hole evolution studies. And in relative or quasi-Wald feedback, one should assume what the IgN ACD looks like. And this is actually extremely tricky because the zero order assumption is one unique ACD for every quasar at every luminosity and redshift. I'm going to show you that this is actually not correct. So, what a UV spectrum of a black hole accretion disk look like? We are back to 2002. This is the work done by Telfer using HST data of a sample of poor stove of more than 184 quasar redshift 1.2. This paper has more than 340 citations, is widely used in the literature, and as you can see, it has two slopes. Is modeled by the continuum is modeled by a broken power law in the near UV, and in the extreme UV it gets softer, with a break at around where the Lyman alpha is. Recent work by Scott, 2004, using fused data. This is a very small wavelength range compared to Telfer, and as you can see, there is no break. This is really hard continuum, 0.56. The sample is much smaller and it's more redshift and lower redshift. And as I say, there is no break. And then there is Shalom. This is the recent work using cost data. 22 quasar, low redshift, and again there is this break at 1,000 angstrom. And two slopes, and it gets softer going from near UV to extreme UV. So, we expect a break in the UV through a black body increment, which depends on the black hole mass and how, and I'm going to show you that this actually depends on how you correct for the IgM absorption. And we expect also less massive black hole to be hotter. Why we do expect this? I'm not going to talk about the shape rationalities because I don't want to get King upset, but this is what's actually happening. So if you assume IgN luminosity, which is derived by accretion, and the particle energy is dissipated locally at a certain distance r, and optically thick medium, which is a black body, Video theorem, then you get this. So the temperature is depending on the accretion onto the supermassive black hole, the black hole mass, and the distance as well. However, the most important parameter in this equation is given by the black hole mass. And just to provide you a few numbers, just to give you an idea, if you just keep 3 Schwarzschild radius with an net iteration of 0.1, lower black hole masses, 10 to the 6 solar masses, would have a temperature of 5, 10 to the 5 Kelvin, 10 to the 8, around 10 to the 5 Kelvin, just to give you a rough idea. So that this temperature is decreasing as the black hole mass increases. And therefore, we expect to see the location of the break changing as a function of the black hole mass. Is what we see. So I just plotted here the absolute magnitude in the I band normalized to redshift 2 as a function of redshift, just to put everything on one plot. And this gives you roughly an idea where the black hole mass on average should be. So 10 to the 7, 10 to the 8, 10 to the 9 for these luminosities, for these magnitudes. And this is where Telfer lies. So the orange and the shaded area is where the Telfer 2002 sample is. Then with a break at around 1100, as I said, around the Lyman alpha, and then we have Scott 2004 using fused data, no break. And then SHA 2012, again a break in 1000. So it seems, actually, that the thermal disk is peaking further into the blue for small black hole masses. And maybe we are seeing the expectant translation, but there is a but. I'm going to show you that this actually depends on several corrections. Additionally, the high redshift range is poorly explored. Only 22 sources have been used in the Telfer sample at redshift higher than 2. So to summarize, the most massive black holes, and therefore the ones at high redshift, are poorly explored. Previous work used oversimplistic, and I'm going to show you which correction I'm talking about, and outdated models for the IgM correction. And these samples are highly biased. I didn't tell you which was the selection criteria for those samples. So basically, they took whatever they find from the archive, which actually tend to be UV brightest and has blue as object, and the selection criteria are certain. So what we want to do, we want to construct for the first time the UV composite of QSOs at redshift higher than 2 with the state-of-the-art IgM transmission correction and proper estimate of the uncertainties using a sample which has a clear selection. So, the sample. The sample is composed by 53 quasars from Sloan, from redshift 2.28, 2.6, average redshift is 2.24. This quasar has been observed by WFC3, and just to give you a rough idea, the signal to noise is about 30 at 30 and 15 angstrom, and all the data has been described in Omera 2011-2013. So this is the composite from Sloan of the 50 quasar that I'm talking about, and this is WFC3 composite, which has this sharp decreasing to Flammable limit systems. So just to put this into context, this is the plot that I showed you before with the 3 samples, and now I can put the sample that I've been using, which is down here. But now we are start exploring this region. So let's go back to the data, and as I told you, I need to correct for the IgM. So I have used 10,000 IgM transmission cursor for a suite of different column density via an MCMC approach, which has been calibrated from quasar absorption lines. So these are the state-of-the-art IgM correction for this sample. And I'm going to show you what is the difference between this correction and the ones that has been employed so far. So this line that you see on top is the correction which has been used by Telfer 2002, which is about 1% over the old wavelength. And this other one is the one employed by Scott. They use a single correction for a broadband or luminosity and redshift. And just to place a line, if I want to overplot all these lines in this plot, all these lines will lie in this very small region. So the corrections are actually extremely small.
But those are for lower redshift objects, right?
Not for Telfer. Telfer has, as I said, high redshift objects as well. The average redshift is about 1.1, and they have quasar redshift 2. So this correction is definitely underestimated. So this is so you have the correction now, you have the data, and then you can correct. So basically dividing the flux for the correction. And this is before IgM correction. I'm just focusing on the WFC3 composite. And this is after correction. And I don't have time to go into the details of the uncertainties, but this is actually how the uncertainty looks like. If you take into account everything, sample variance, shot noise, everything. Everything is placed in there.
Also the uncertainty due to the IgM correction?
Yeah, everything. Everything's in there. And now I can give you some numbers. So this is again the Sloan composite, the WFC3 composite corrected for IgM correction. We can fit a continuum in justifying masking the lines, and it seems that a power law here fits pretty well with data with a slope of minus 0.63, but it doesn't go through the composite at lower wavelength. And we actually model the break through this formula, which is around 1 Ringberg. And the composite gets softer at shorter wavelength, around minus 1.9. So just to give you some numbers to use. So now I'm gonna do a comparison. So this is again luminosity as a function of frequencies, how you place the two composites, corrected and not corrected. I have also added the Galex data, so I have stuck the Galex data for this sample in order to increase the wavelength range, and I can put Telfer on top. I have normalized Telfer to the optical, like 2000, roughly 2000 angstrom. And as you can see, The IGM correction in Florence, they said, is less than 1%, so in the forest, the correction should be at least 5%, so this is 10% difference. And a shorter wavelength, where there are only quasar high redshift contributed, the correction is much higher than 1%, it's 80% actually. So this composite is underestimated at all wavelengths. So just for completeness, I'm going to show you very quickly where the Shaw composite is and the Scott composite, which, as I tell you, doesn't have any break, but it doesn't go blue. So it seems that it's quite a difference depending on the luminosity. They say these composites are probing different luminosities and different redshift. And in the last part of my talk, I have a couple of minutes, right? In the last part of my talk, I'm going to show you, I'm going to forget about all the other composites. I'm going to use accretion this model to actually model the composite I've shown you before. So I've been using the DAN 2012 accretion disk models, which model again, I'm using model too much. Outer disk in red, which means as a color corrected black body. The inner disk is shown in green, where the emission is Compton upscatter, a fraction of the emission of Compton upscatter, and the X-ray colonna in blue, where also a fraction of the emission is Compton upscatter and gives you the power low tail at higher energy. So we can start playing with these. The data tells me that the black hole mass is around 6×10 to the 9 solar masses. The azimuthal ratio is 0.35. From XMM data for a couple of them, I have an estimate of the photon index, which is 1.9, and this how accretion disk model will look like for the data. I just fixed the model through the data. But these black hole masses may be uncertain since this sample is a high redshift, so you can start playing with black hole masses to see if something changes. You can increase the black hole masses, you can double the black hole masses and then decrease by the same factor the Eddington ratio. And this is what gives you the red curve. If you decrease the black hole mass, this is the green curve, and the Eddington ratio, if you increase the Eddington ratio by the same factor, this is what you get. So basically, similar or like quite different black hole masses depending on the spin. So it's not only the black hole mass that is giving you the big blue bump. So far I just told you that the black hole mass is telling you where the position of the peak is. This is not actually the whole story, because also the spin of the black hole changes, and you can tweak the spin in order to get a very reasonable accretion disk model for this data. And I'm going to conclude. So current estimates of the IGN SED do not properly take into account IGM absorption, so we are actually in an excellent position to do that. I'll show you the first UV quasar composite at high redshift with proper IGN absorption correction, and we get softer extreme ultraviolet continuous, then low luminous, low redshift, and low micromasses quasar samples. And the peak of the big blue bump does not depend on the black hole mass only, but also the spin is involved. And
Can you say how you did the IGM correction?
okay, this is actually it's kind of complicated, but this IGM transmission function has been modeled using the data that I've shown you before. So basically from the break, you have an estimate of the optical depth. Then through some assumption, you estimate what the continuum look like. Then I have several of them, so there are different realization of the same source for estimating the uncertainties, and I have also different realization of the IGM transmission correction depending on the column density.
You do that with your own data? You use
This has been patterned for
Statistical
the
correction though.
right.
The curves that she showed all go through all available existing absorption line measurements for the column density distribution.
Right.
Okay.
Including the column density distribution of H1 and mean-free path, the forest,
So
etc.
what about the QSO not being in a random place in the universe? Did you take that into account?
Using the
The mean free path I've seen from a QSO will be shorter than the mean free path of the universe.
Well, no one's actually demonstrated that that's a effect is real. It's certainly a concern, though.
Chuck has observed it.
Well, there are other reasons why Chuck and Xavier's points don't agree. There are other explanations for that difference, but I don't think that's a huge effect.
It's a factor of 2 according to the simulations, depending on the mass of the QSO, or the mass of the halo hosting the QSO.
So you have composite spectra, not, they typically have like 20 to 50 quasars in there. So can you say something about the quasar to quasar variance? Do you look into that? Is that large, or basically?
I mean, this is encapsulated in the uncertainties. The quasar
that
variance,
sits in
yeah,
there?
yeah.
But are your data consistent with your sample of quasars having a universalicity and everything else just coming from
Yeah, this
IGN variations or other things?
well, this is the point, right? Eventually you want to extend, I've just done this work for high redshift quasar, but eventually you want to do this also low luminosities, low redshift quasar samples. So I don't have a really comparison sample to do to answer this question. So you want to extend this at low redshift.
So we have another tracer of what the spectrum is below the line of limit, which is the emission lines themselves. Right? So to get certain ionized species, you need radiation spectra of certain particles. And the ratio of these might give you a handle on what the spectrum is.
Right.
Thoughts of looking into this?
What I've done was to compare the equivalent width of some lines with what has been expected from photoionization model using Cloudy, for example, Basking et al. 2014. I've actually few slides on this, but I prefer not to show that. But they actually do agree if you use a soft ionizing continuum. So the equivalent width are in very good agreement. So I'm not missing photons.
Okay, if there are no more questions, then let's thank Elisabeta again.